In this video, we're going to talk about symmetry and graphing. So we have three tests for symmetry. Remember when we were talking about rectangular equations, we had three things we checked for symmetry also. We checked with symmetry about the origin. And we said if we were symmetric about the origin, f of negative x is equal to negative f of x. We checked about symmetry about the y-axis. So we said f of negative x would be equal to f of x. And this was the definition of an odd function, whereas the second one is the definition of an even function. And then if we had symmetry about the x-axis, okay, that means we didn't have a function. Because remember, if you're symmetric about the x-axis, maybe something like this, x equals y squared, sideways parabola, that means that it doesn't pass the vertical line test, so it's not a function, but you still could have that kind of symmetry, right, for something that's not a function. And that means for every x value that you plug in, you're going to get two y values, and they're going to be the same y values. So we have three different types of symmetry in rectangular. Now let's talk about the symmetry in polar. So kind of follows the same idea. We could have symmetry with respect to the pole, which would be similar to symmetry with respect to the origin. So how do we test that? Well, in the polar equation, we're going to replace r by negative r. And if we get something that's equivalent, then we know we have symmetry with respect to the pole. If we want to test for symmetry with respect to the y-axis, so we're really thinking about that line theta equals pi over 2, that correlates to the y-axis in rectangular. We're going to replace theta with pi minus theta, and we're going to use some of our formulas from chapter 7, sum and difference formulas, to see if we get something that's equivalent. If we get an equivalent equation, then we know we have that kind of symmetry. And if we want to test for symmetry with respect to the polar axis, we're going to replace theta by negative theta, see if we get something equivalent. If we do, we know it's got that kind of symmetry. So here's the thing, though, with these types of tests. In polar, these conditions are sufficient, but not necessary. So what that means is that if this works out, if we do the replacement, if we get something that is equivalent, we are guaranteed to have that kind of symmetry. But if we don't get something that's equivalent, that doesn't mean that we automatically don't. That just means we need to check the graph. Okay, so it's sufficient, but it's not necessary. Okay, just because the test fails doesn't mean that that symmetry doesn't exist. So let's do a couple of examples. So my first example, I'm going to look at the function r squared equals 2 minus 3 cosine of theta. And we are going to start with that first kind of symmetry, that x-axis symmetry. So I'm going to, or polar axis, I'm going to replace theta with negative theta. And I'm doing that in this equation. So I'm going to get r squared equals 2 minus 3 cosine of negative theta. Okay, but we know that cosine is an even function. So we're going to get 2 minus 3 cosine of theta. Okay, notice this is the same thing we started with. That's what we mean by equivalent equation. Once we do all the math, do we get the exact same thing we started with? If so, we say that this function is equivalent to this function. So then what we know is we definitely have symmetry with respect to, I'm going to abbreviate that, WRT, the polar axis. So let's check the second type of symmetry. We're going to check symmetry with respect to the line theta equals pi over 2, which is the y-axis. So I'm going to have r squared equals 2 minus 3 cosine of pi minus theta. Now, work with that right-hand side. I can use the difference formula for cosine here, and that's going to be cosine of pi cosine of theta plus sine of pi sine of theta. And we know that cosine of pi is a -1, and we know sine of pi is 0. So r squared equals 2 minus 3 times negative cosine of theta. So we're going to get that. Okay, that is not the same thing that we started with. So we would say the test fails. So we need to check the graph to see if we have that kind of symmetry. And then the last one, we're going to replace r with negative r. So I'm going to have negative r squared equals 2 minus 3 cosine of theta. R squared equals 2 minus 3 cosine of theta. And that is the same thing that we started with. Anytime I take a negative value and I square it, I'm always going to get a positive. So we say that we do have symmetry with respect to the origin. All right, so for the test, we pass the test for symmetry with respect to the polar axis and symmetry with respect to the origin. So we definitely know we have those types of symmetries. Our test failed for the second one, which was checking symmetry with respect to the line theta equals pi over 2, but we won't know for sure until we check that graph. So let's look at that graph in Desmos. I'm going to go to Desmos. And I'm going to graph my function. So when I graphed this one, Desmos kept giving me an error. You saw the little triangle over here. When I did r squared is equal to 2 minus 3 cosine of theta. So if we take the square root of r, remember, anytime you take the square root, you have a positive and a negative. So you can see both halves of the graph here. So we can see the symmetry that we have that we confirmed over here with respect to the polar axis and with respect to the origin. But notice our test failed when we checked that second one, which was with respect to the y-axis. But if we were to look at that graph, we actually do have symmetry with respect to the y-axis. So the side is symmetric to this side. So even though the test failed, then the graph showed that it has symmetry. And sometimes that will happen. We're working out, we'll get something that fails, and then we check the graph and it will actually have that kind of symmetry. Remember, there's sufficient but not necessary conditions. Let's just do one more. You may want to pause the video, try it, and check your answer. So let's start with the polar axis. With the polar axis, we're going to replace theta with negative theta. So when we do that, we're going to have r equals 4 sine of 2 times negative theta, which is going to be negative 4 sine of 2 theta, okay, because sine's an odd function, remember. So this fails the test. So let's try symmetry with respect to the pole. That's where we're replacing theta with pi minus theta. So we're going to have, oh, just kidding. Hold on one second. Actually reading r with negative r when we check with the pole. So we're going to have negative r equals 4 sine of 2 theta. Well, that's not the same equation that we started with, so this test fails. And then if we check with respect to the one theta equals pi over 2, that's the one where we're replacing theta with pi minus theta. That's the one that's going to take a little bit of work for us. 4 sine of 2 times pi minus theta. So that's going to be 4 sine of 2 pi minus 2 theta, and that's where we're going to use the sum and difference formulas from chapter 7. So this is going to say sine of 2 pi cosine of 2 theta minus cosine of 2 pi sine of 2 theta. We know sine of 2 pi is 0, and cosine of 2 pi is 1. So we have 4 times negative sine of 2 pi, which is negative 4 sine of, sorry guys, that's supposed to be a 2 theta. Erasure is not working for some reason. This is going to be a theta right here. Okay, but that's not the same thing that we started with up here. So the test fails. So in this case, all 3 tests fail, but let's check the graph for this guy because we know that's the equation that arose. So I'm going to go to Desmos, and I'm going to graph that one. R equals 4 sine of 2 theta. And you can see a rose with 4 petals, and it does have symmetry with respect to the x-axis, the y-axis, and the origin. So we've got all 3 types of symmetry. So even though the test failed, we still have the symmetry. But remember, the test is only sufficient. It's not necessary. So if a test fails, you have to check the graph to see if it has that symmetry. If the test works, then you're guaranteed to have that symmetry.